Today, I think there's various things that we should go through, but I think the first one is data structures, and so I want to start out with a discussion of data structures for problem 3. So as we mentioned a week ago, the network is what compiler writers call a DAG, directed acyclic graph, in which the elements are classified into inputs, gates, and outputs, and the gates have 2 inputs that have previously been computed, and you can write it in straight line code as we did in the handout. And the first question is, how do you want to represent the DAG inside the machine? So what are the winning methods for this that people have? Somebody want to speak? Don't all speak at once. Just all smile. That's nice.
We're using Lisp.
You're using Lisp. That's the data structure. In other words, put yourself into somebody's preconceived idea of a data structure. Right?
Data structure is each gate has a symbol, and in its property list are a number of fields. And
so each
gate has a type.
Okay. So a gate type like exclusive OR?
Right. Mm-hmm. Or and it has a.
And the property list would say what? Like
type and.
What would it look? Is it easy to do it? To do this one, for example?
Yeah, you'd have 3 gates. Oh. You'd have 3 gates, I0, I1,
inputs.
And yeah, those are inputs. Their type would be input. Same. They would have a field outputs.
Why don't you put some parentheses in there if there's Lisp? Maybe they write Lisp without parentheses nowadays, but
oh well, yeah, okay. It's just under the property list, and here you would get its output would be say gate 0, and then I won't do the whole thing, but then gate 0 would have.
So, you know what you're saying, where X is used, and this is gate 0,
right?
And this is gate 1.
Okay. Yeah, right. You would also
okay.
Have and gate 0 would then.
It almost looks like garbage out, garbage in.
Would have type XOR and input
I0 and I1, right?
Yeah. Here I should write it like this. The inputs are nil here.
Okay.
And right, I0, I1, and the output. So where is
A is used in gate?
We'll call this 2
and 3. Yeah. Okay. Okay. And then
any other fields that you want to put in there later.
Okay. So for values or something like that.
Right.
Mm-hmm. Okay. Is that what everybody uses, or what are the other ideas that people have? Everybody's using Lisp for this one?
No, I'm using C, but we're using C, but it's more or less equivalent to that, where you have a type and you have 2 inputs and then a list of outputs.
Okay, so you're keeping with each one both inputs and outputs, even though it's redundant to keep the outputs. I mean, you could always calculate what the outputs are by looking at all the inputs. What?
Yeah, but you'd have to look at every gate to see.
You'd have to do it over and over again, yeah.
Yeah.
That's why, but I meant redundant means that we've got extra things in the data structure that aren't strictly necessary as far as having a representation is concerned. But if you want to, if you want to, you look at what you're going to be doing with the data structure and you add extra unnecessary redundancy, as they say. This is the division of unnecessary redundancy division. Okay, the helpful redundancy. Okay. Now, then, but how do you decide what the names of the gates are going to be?
The symbol under which the gate is.
Yeah, G0. Where did that G0 come from?
The gates are numbered in the order in which they're generated, and they're generated by the procedural framework, just like the one you gave us.
Okay. You got some code that runs through and generates gates, and
There's a basic. There are three basic procedures: one which makes an AND gate, one which makes an OR gate, one which makes an XOR gate, and they're called in the appropriate places in each of the modules on the sheet, and they generate the gates. They take two inputs, and they look at the
input might be like I0, and 0 might be another input, right? I mean, 0 is
Right,
the
right.
constants are somewhere in your data structure too,
Right.
and then it doesn't generate a gate.
It doesn't generate a gate if
If
the output is predetermined.
Yeah. Okay. Right. Now okay.
And then the gate generators then go back and put themselves into the output lists of their inputs.
Okay. So when this one, when you have a little generation procedure that says generate me an exclusive OR gate from I0 and I1, which then created this part of the structure and added G0 to the output list of I0 and I1. Okay. And then do you have a list of all the gates too, or something like that? Then at the end, I'm wondering about two things. One, is there a definite ordering of the gates that you can use later on in an algorithm? Some gate is before another gate, or does that make any sense?
See, since the gates are always generated such that the inputs are generated before the gate itself is generated.
Yeah.
You have a kind of topological order on it.
Yeah, that's in any acyclic network graph. There's a way to linearize it so that the inputs are before the gate,
Right.
and the outputs are after. Yeah.
So if you take the gates in order of the numbers,
Okay.
you can do a straight evaluation that way, for example.
And how many do you get altogether when you do that process?
I can't remember.
Anybody remember?
You get somewhere in the high 400s or something, and then
how many gates did you get by eliminating 0?
that was the high 400s, and then when you eliminate gates with dangling outputs, I think you get 401.
Okay. I got 417.
I can't remember.
Is that right? Okay. Yeah, that's it. Is that right?
And you also eliminate the ones which have the same input both from left and right.
You get 16 gates. This happened? You had a.
I don't know. I just.
Oh, you had it in the program. Oh, okay. So it's.
I think all of those do eventually go.
4 and 1. Yeah, 4 and 1. Okay. Now I tried it, by the way, on 32 by 32 multiplication, and I got 1,747 gates before removing the output ones, and then it went down to 1,722. So this number 401 goes up to 1,722 when you double the number of bits. So you get a parallel 32 by 32 multiply. I'm sorry, that's a 16 by 16 multiply. And a parallel 32 by 32 multiply I tried also, and I got 6,972 gates before throwing them out, and then 6,933 at the end. So the 6,933 again, it goes up by about a factor of 4, as you can imagine. That's just at the very beginning. The very first round is the n squared, right? I mean, just to multiply all the xi times yj. Is giving you most of the gates, and that was depth 34. So you could have a 32 by 32 parallel multiplier with 64 bits of output and 34 levels of logic with the same construction, and about a little less than 7,000 gates altogether, for what it's worth. Now let's see. We also had this possibility that the gate might be, that there might be a gate that has a solid 0 output. Is that right?
And, all right. Well, I guess
there seems to be one each level above from 3 up.
Okay. Now, yeah.
There's another gate behind it which only feeds into that gate, so you can't check faults on either of those gates.
check 0.
Oh, now say that again. So you say, first of all, you tried 3 bits, 4 bits, and up to.
I tried 3 bits, 4 bits, and 5 bits, and after that my program gives up.
Okay.
It finds gates.
And there was a gate that was solidly 0.
Yeah.
Okay. So presumably on 8 bits this will happen also.
Probably. Which means if you try to detect all stuck at 0 faults.
Which means that if we try to detect all stuck at 0 faults, we're not going to be able to detect one of them because it will. Yeah. Now, what was the other thing you said, that this gate it's stuck at 0? I mean, it's always 0.
There's one gate that's always 0, but there seems to be another gate which you can't detect the stuck at 0 fault, presumably because it goes through the first gate.
It's one of the inputs of the stuck at 0 gate.
The always
0 gates.
Okay. So let's see. So
it has that gate as its
I'm
own
going to erase
output.
this. This is an AND gate, I betcha. And so there's some AND gate that comes in here, and it turns out that it's always 0. Right? Now this one, you're saying that actually this one is used in it's used in an exclusive OR gate afterwards, and some other stuff.
It actually goes into an OR.
What?
I think
okay. Well, it might be different in a different one.
Well, it doesn't really
Let's
matter.
take a look at the. But I don't understand what you said about the that. I mean, I can understand why this one would never be stuck at 0. Why you could never detect this one stuck at 0, because it's
that only feeds that gate.
Okay, so you say that there's a gate here that comes here only.
Right.
Mm-hmm.
Such that
And there's no way of telling if it's 0 or 1 because you'll never.
Because if this guy comes out with a 1,
the other one will always.
guaranteed to be 0.
I'm going to put that 0. Yeah.
So you can't detect stuff at 0.
Is this true of the circuit, of the 8-pole circuit, or just of the small cases? Right?
You'd have to check all possible inputs. And nobody's done that yet.
Okay. So you're saying that if this one has only one output, then there would be we'd be stuck because this one has a known. Yeah, anything that has to go through this critical path would be there.
You can still detect the stuck at 1 on that upper gate, but you can't detect the stuck.
Okay, well, let's see. The one thing we could do is have a proof that it's always 0 and then remove it from the circuit, thereby having fewer gates, right?
But you have to first of all know which gate it is.
Yeah. Okay. Well, let me see. What do you do? But I want to do this democratically. What do you people think we should do? Say that we have 401 gates, and we detect all the stuck at faults that are of those 802. We detect all the detectable ones, but we assume that the circuit is actually built that way, so that if there's redundant calculations, the circuit is still still supposed to do it. That's one approach. Let me explain. For example, if this was a plus coming in here now, but we know that this is 0, and this is some other gate here, I can still have a fault at this exclusive OR, because this XOR might still be stuck at 1, the same as this one might still be stuck at 1 or 0. And so that gate is actually there, and so we would have to detect a fault for that one as well as a fault for this one. On the other hand, they're sort of equivalent. I mean, we're just giving ourselves more chance for fault. And maybe if we were actually designing circuits, we would have while testing while doing our theory of this circuit, we would realize that one of the gates is redundant. So we saved 2 gates. I mean, we saved not only this one but this one.
Actually, the one I guess.
Well, if this one is feeding only to that, you could get rid of it too, because it doesn't have any. I mean, if we get rid of this one, then there's no outputs for this guy. Yeah. Now I could tell the class which gate this is, and then you could say go down to 399 instead of 401, or you could leave it at 401. And I mean, what would you kids rather do?
Well, I was thinking of something else. If the gate before it is stuck at 0, it's not a fault in the circuit. I mean, the circuit will still work properly. So it's not as if. So if the actual idea was to test, if the idea was to test the circuit to see if it's always going to work properly, then it doesn't matter if it's stuck at 0. So it isn't really a fault.
Okay,
in that sense.
So we redefine the question saying just here's the circuit, find all the faults.
So really you have 800 faults rather than 802.
No, but
only you don't know that we need to.
Well, you're presuming that there's somebody with only one input.
Yeah.
Well, yeah.
Let me tell you what the fact is, because I happen to have the circuit here. Let's see. It identically 0 is the end of 721 and 718. 721 and 718. They're both used in two places. So this situation doesn't arise. There's another outlet for for both inputs.
Are you looking at the circuit before it was at dangling outputs?
I'm looking at the circuit, the 401 gates.
Oh, okay.
Circuit. If I've done this correctly, my programs, over the years I've made 1 or 2 bugs in my computer programs.
Out of 2 independently written programs agreed there were exactly 2 gates that you couldn't detect stuck at 0.
In the 3 and 4 and 5 case, yeah. Now this is another case. Let me tell you that it was a surprise. At first I looked at this and I said, oh, of course, this one's always going to be 0 and then I realized that it was going to take me I think it's a fairly a 1 or 2 page proof to show that this particular one, because it was a different gate than I thought. What's happening is that you got these numbers A1 through A16, which are your what are the initial partial products? A1 to A8, I guess it is, huh? Or A0 to A0 to A7. A0 to A7 are the initial ones, and then we take A0 plus A1 plus A2 is equal to A8 plus A9, and so on. The last one being A. What is it? A. Let's see, I got it written out here. A18 plus A19 was equal to A15 plus A16 plus A17. And so we started out with 8 inputs, and then after 6 of these reductions, we have two left, A18 and A19. Well, it turns out that the bit that's 0 is the high order bit of A19. It just turned out that if you look at the leading bits of A15, A16, and A17, I was getting 0, 0 always for A15, and 0, 1. 0 A bar, 0 X bars for some X, for A16, and X0 for A17. And therefore A19, which was adding this column and deciding whether or not there were at least two ones in it, was guaranteed that the leading bit of A19, which is the carry from this column, was always 0. And that's what it turned out to be. Well, now you have to look. This is A15, if I'm not mistaken. I might have these numbers wrong. Yeah, I'm sorry. This is A13. Oh, no. A17, A16. Yeah, I think it's A15, A16, A17. But my proof might be slightly flaky, but something like that. I might have renumbered things as I went. But based on the fact that these original inputs are known to come from multiplication, this is true. It's not going to be true if you start with any 8 numbers. That A0 is known to start out with leading zeros, and A7 has one 0 and trailing zeros. A6 had 2 leading zeros, and something like this. But in order to show that this leading bit of A19 was 0, I believe it's necessary to know that A6 and A7 are almost the same, except shifted left 1, or both. A6 and A7 can either be 0 or the same as the other one, shifted over 2. And by using all that fact and putting it into the circuit, it turned out that the leading bit of A19 had to be 0. Well, this was now this might generalize to arbitrary length of circuits, but that's the funny one that is 0. So the facts are then that we could simplify the circuit, but I'm not sure what you people how you would like to recast the problem.
I don't think that this in general would be a valid way of doing things, merely because if with an arbitrarily complex circuit, it might sometimes be very difficult to detect the fact in the first place that a certain thing is not going to matter, and essentially that it's always going to be at a certain value. So I think the programs or whatever that are doing this, which are trying to find such a cover, should themselves be capable of at least pointing out which are the probable ones which cannot be checked, and then maybe one could check them by other means.
Oh,
I mean,
okay.
you have to essentially solve the problem. The question is whether you do it before or after you try finding this.
Yeah, that's what I think we should all be working on the same problem. That's what. So I want to get to an agreement among. We're going to take a vote, and we're going to use majority rule on this. So we're all working the same problem. Now, and John's point is very well taken. It says all we have to do is find a set of x's and y's, so that if it multiplies these correctly, then it multiplies all x's and y's correctly. And that formulation of the problem is independent of the number of gates in the circuit. There might be lots of other gates in there.
753.
Yes. Is that what it is without eliminating zeros?
Yeah.
What?
Yeah.
Yeah, okay. 753, I thought it was even more.
754.
Okay. So, I never got that count because I eliminated them as they went. But, okay. Well, there's a matter of whether you count 0 goes to AI as a gate or not. I guess it isn't. Okay, so that's one way to state the problem. Otherwise, we would say reduce the circuit to a simplified circuit and then solve the problem on that one. So how many vote for the first alternative, leaving it at 401 gates? And we got 1, 2, 3, 4, 5, 6, 7, 8. How many vote for the second alternative, simplifying the circuit first and then solving the reduced problem? We got 1, 2, 3. How many are asleep? 8 to 3 and 4 asleep. Okay, so the 8s carry it. So we're going to go with the 401 gates as it is, and we'll just find a minimum number of test cases that will suffice to test whether or not it either multiplies everything correctly or has more than one stuck at fault, assuming that stuck at faults are the only kind of faults. Andy?
Well, but then won't all the groups have to run the same really brute force large program and kind of drag Navajo down? I mean, is there a way to do it other than brute force?
Well, this particular proof of this, that this was always zero, it could have been discovered by a heuristic search, I believe, because I did it by hand, looking at this bit of A19, and it required some other bits, and it only went down about 8 levels, and I could get it. So it wasn't necessary to go through. I believe I could do by hand this thing on the corresponding thing on a 32 by 32 circuit. I'm not volunteering to do this, but I think it could be certainly done by machine. It wouldn't require going through all 2 to the 64th combinations of 32 by 32 inputs, 32 plus 32 inputs, and to determine that a corresponding gate in the larger circuit is a constant zero.
Right. The idea might be to just have whatever heuristics you use to check some proportion of the inputs anyway, sort of just indicate that this is a possibility, a likely possibility, and then you check it from there.
Yeah,
We didn't say that to be done
I have a feeling that a variety of methods is going to be useful on this problem. I'm worried about bringing Navajo down too. I mean, there are lots of ways to work on problems like this that will be bad, and I have tried some of them personally. In fact, I had this one heuristic search that was using forward and backward propagation, as we had in class a week ago, and it worked fine on most of the gates, and then on one of the gates, just for fun, I let it run until I shut it off after an hour. I mean, it was sail, but just to see if it would ever, converge, and it didn't. I mean, and I have a dare with Mike Geneder to see if any of his programs can do. So, but on the other hand, other ones, it worked amazingly fast, and almost most of them. So I turned out that when I was exploring this problem, I had only three days to work on it, but I worked solid on those 3 days. The final solution I came to was with a combination of methods. No one method was used for the whole problem. Maybe you'll be able to find a more universal thing. Well, let me see. Now, so we voted, and that was and the decision was that we can all agree that we're working on the same problem if we have these 401 gate network, and it's easier to agree on it. So that's the problem we'll look at. It has this gate in it, and also this gate, even though neither one is strictly necessary. Okay, now, Rich, you said that you wrote in C, but it was equivalent to this. Well, if anything is equivalent, I mean, all
it's the same basic structure where you have a node in a graph for each gate, which has inputs and outputs, which are pointers to other nodes.
Right. Let me show you one other possibility. Just to if we did it with arrays, we can imagine an array that has the inputs are the numbers that are less than or equal to some global variable m, say number of inputs, and then the gates are represented here in the out. So this is inputs and gates and outputs, and then for each thing we could have a type field or an array called where type of 1 would be the code for an input, type. Let's suppose that, well, there's many ways to do this, but let me just give one that that generalizes to compilers. There's lots of ways of doing it, but here I would put one way is to use three words for every gate here, where this one would say, or 4, 5, and 6. This would really be gate number 6. This one would be exclusive OR. This one would say fetch, and this one would say fetch. And then there would be an operand where this one says fetch 1 and this one says fetch 2, and then XOR is the result. Then let's see, I'll do a couple more and show how this could work. We have always, every gate is a bunch of fetches, so if it's inputs and then it's the operation fetch exclusive OR again, where this one fetches 7 is fetch 1, fetch 2, and then fetch 10 is to fetch A, which is this, 6, fetch Z, which is 3, and exclusive OR. Now, in these other fields, we can use that for the list of outputs, and so every gate, the XOR and XOR and input can have a field here which points to the first use of the thing. So, for example, variable 1 could point down here to where it's used in this fetch instruction, say to 7. 4. The last use, I guess. And then this 7 could point back to 4. There's an auxiliary pointing field, let's say, if you wanted to keep lists. So that this could point to 7, which could point to 1, point back to 4, and then there's nothing after that. This is one way of representing the list of outputs in a simple linked fashion. When you compiled this part of the network, this was pointing to 4. But then when you added this gate, you added this guy onto the list, and it referred back to the previous one. The list could go in either direction, but probably pointing back is just as easy. Now, similar to this exclusive OR, A would then be used in 10, and 10 would point back to this, and the outputs would all be fetches, and so everything that's used in an output would get moved here. That's I haven't filled in all these numbers, but I think it's fairly clear that you could do it with ordinary in Fortran if you had to, by 3 arrays like this, and then you could have other arrays for value or labels or whatever else you want to be calculating on the thing as it goes. Now, but that's not the only data structure question in here. If we're doing a heuristic search, at least maybe I'm naive, but if I'm going to do a search that goes forward and backward as we did in class last Tuesday, I'm solving what are the typical problems that I'm working on. Let me go over here. I have a gate that maybe it's exclusive OR gate or something like this, and I'm saying that this gate is, I'm going to assume that this gate is 0, and I want to find the values of the input that's going to make this gate 0, and there'll be several. I'll know properties of other gates too. So if this one is 0, then what do I know about the two gates that feed into it?
They have the same value. That
they're the same value. So this is somehow alpha and alpha. That these two are equal. Right? And then suppose I have an OR gate here, and there's some gate like this. I also have a value Let's see. Now let me make this a 1, just so that I don't need so many. So if it's a 1, then I know that this is alpha and alpha bar, that the two inputs are whatever, we don't know what they are, but whatever they are, they're different. And similarly here at the AND gate, if this one is beta, then this one is going to be beta. These two are known to be equal because this input is 1 to the AND gate. Okay? And when you have exclusive OR gate, if this was an exclusive OR instead of an AND, and this was known to be beta, what would this, and this is 1, we put beta bar here on the thing. So it looks like the kinds of information that we want to propagate if we want to do an efficient problem solving on this thing would be, first of all, to know that a gate is known to be or assumed to be constant, and secondly that we would know or assume some relationships between different gates, that these are actually equivalent or inequivalent values. Now the second, according to Genezareth, nobody has put the second kind of information into their analogous programs that they were using with circuits. But if you got a lot of exclusive ORs, it seems like that could be a big win. The second kind of information, saying that we have equivalence classes between things. Now this beta might propagate along ways. We might have betas all over the place, and we might be able to combine them somewhere else to say that beta and beta bar is known to be 0, for example. If you get two inputs to an AND gate, one is beta and one is beta bar, you know that the AND is 0, even though you don't know what beta is. Okay, so what's a good way of representing information that two values or n values are related to each other in this way? Does anybody have a good idea for that one? Everybody, now I don't even get smiles. I mean, at the beginning of the day I got smiles. No.
That's because we all knew and were not saying.
You all knew at the beginning with the smiles, and now nobody knows, and
we're still not saying.
Okay.
Kind of silent. You could have each value on each line be a function of some certain set of variables.
Okay.
There's
A set of variables, yeah. Okay.
Do you know if conversion?
If conversion, no.
No.
This is.
It's a technique
This
used
is
in
for-
optimizing compiler.
Yeah, but to get rid of conditionals, if sounds like it has to do with ands and ors. Like if x and y, and you know that x is false, then you don't.
Right.
And you don't evaluate y, unless you have to.
It doesn't
side
have to do
effects,
with not evaluating the y, but it's more like in data flow analysis, you know, if you're at some point midway down the control flow graph of a program, and you've taken several if branches, you know that a bunch of conditions have to be
Conditions
true,
are
that you
true,
followed down.
yeah.
And in choosing in representing the condition of the data at that point in the program, it's like the intersection of a bunch of different things. And you could represent
General logical quality. Yeah, this is a very special case where we just have equals and unequals. In other words, I have a bunch of relations and I say x1 is equal to x2, and then I say x3 is equal to x4 bar, and then I say x2 is equal to x4. Now, what's the relation between x1 and x3? So in other words, I have two variable equalities here, and it's always with bars and non-bars. Now from this I can deduce the relation between x1 and x3, because x1 is equal to x2 is equal to x4 is equal to x3 bar. So I want to quickly know x1 is equal to x3 bar. But there's a data structure that will tell me this fairly quick.
Union find.
Union find, yeah. Okay, the union find algorithm is a typical name for for the class, for the keeping track of the equivalence classes, where we add another feature to union find, where we say where we have things that are equivalent, but some of them are negated with respect to the others. And so what we really have is an equivalence class here: x1, x2, x4, x3 bar, x4 somehow are known to be equivalent, and we want to be able to propagate across equalities quickly. All right. Now there are many ways to represent equivalence classes, and the books have a variety of discussions of this, and there's one of them that I wanted to mention, especially because I think it's the easiest one to undo. You see, if we're going to be exploring this circuit, and we're going to be making hypothesis where we have to branch, it's sometimes desirable, I guess. You either have to save the world, so that if the branch you took was unsuccessful and you have to try again, start over from scratch, or you have to have a way of undoing the decisions that you made, undoing what changes to the data structure you made based on an assumption that later proved to be false. So I want to show you one a structure that's guaranteed to be, that's known to be very efficient in practice, and also easy to undo for this problem. And the idea is very simple. If you have things that are known to be equivalent to each other, let's suppose I'll represent them by circles. We just have them pointing. We just have each one pointing to the next guy in the list, and they also point to a header node. So each one of these also has a pointer to the header, which I won't draw to the header, but the header here contains it has an address that you can say that they're all pointing to him, and the header says 4. It also tells how many there are in the ring. The header, I don't think has a pointer to anybody in the ring. I think we can get by with only pointers to the header. Then there's another one over here that I'll say these people are also known to be equivalent, and they have their header, which equals 3. So they're also pointing here. Now, let's forget the complementing part of it first. We can represent the complemented part by having the negative of the pointer here, for example, or another bit in this. Anyway, some other bit in this representation, saying that this is equal to the complement of the other one if you don't have the same bits. But now, in order to make two things equivalent, first of all, it's easy to tell whether two things are equivalent because you look at the pointer. If they point to the same header, then they're equivalent. If they don't point to the same header, then they aren't. Okay. Now, suppose somebody gives you an equivalence, which is called the union. There's a union and a find. The find is to find what equivalence class you're in. That's immediate. It just one reference tells you what equivalence class you're in as a pointer to the header. The union is to take two of these rings that are not equivalent and to merge them into one. And what do we have to do in order to make these two equivalent? Well, we got to change two rings into one ring, and we also have to update some of these pointers. Okay. Now that's where the reason for storing 4 and 3 comes along in here. We can look at those and see which one is the smaller, and use that and choose to update the pointers in the smaller one. And so suppose this is node P and this is Q, and somebody says now P is equivalent to Q. Then let's forget about the Q bar would be another thing, but there's a corresponding thing for Q bar. Okay, now what changes have to go in the data structure use another color of chalk. Orange chalk will be after. What's the smallest number of changes I can do to this data structure to make the to represent the fact that P is equal to Q now? Or easy.
1.
Remember, I'm giving pointers to P and Q, and I don't know who points to P. I don't.
There'll be 4. 4.
Well, tell me what they are. Just all.
I mean, you break the connection at some point on any one of them. Let's say on P.
Yeah.
Break the out connection. Connect it to Q.
Connect it to Q. Oops.
Connect it to Q, remembering that essentially connect it to the one next to Q. Remembering that Q is the
this one here?
No, connect it to
This
the next
one? Yeah. All right.
No.
Okay. This one. I know what that one is because Q is pointing to it. I have a pointer to that one because Q points to that one.
Sorry. And now you make Q point to the one next to P.
Yeah. This always is true, by the way. If you have two cycles and you interchange the pointers, you always merge the cycles together. This is in a permutation. If you have two disjoint cycles and you multiply by a transposition, that's equivalent to changing two of the pointers. So now we got a circle. It's a funny thing, but it does tie everything together. And it was immediate to how to get that because we just interchanged link of P with link of Q.
You got it.
Furthermore, we have to. Yeah. So first of all, we got to modify these guys by going around the loop to Q, in which case we could in fact figure out if we wanted to who was pointing to Q while we were doing that. So we could have broken this one in another point, and we also have to change this to 7 by adding the two signals together. Okay, Ari?
Why do you need the linked list at all? I mean, what are you using it for? I mean, the circularly linked list.
Anybody know the answer to that one? Why do we keep? Why don't we just have pointers all the way up?
Otherwise, you wouldn't have been able to change the header pointers.
Yeah, the circular linked list is helping us to telling me which pointers to change. Good question.
I just thought that instead of storing in each node a pointer to the header, the header itself could be let's say a node which contains a value. Okay. And if both of them are just headers which contain a value, right? You just change the value of the other header. And
that leads to another important class of union find algorithms that you keep on going upward until you get to so that the find algorithm searches maybe more than one step. That's what you mean. Yeah. And it's a very interesting theory of this. We could spend several weeks just discussing union find algorithms because, for example, Tarjan has proved that a certain one has a worst case that's you need more than the number of things in the universe in order to make it go more than length 5 and things like this. And there's Andy Yao and I have proved that this particular kind of scheme is linear on the average. That is, if you take equivalences on the average, then the average amount of work per update is something like 1.5 updates or something like this. In the worst case, it's got to be n log n, because if you're always merging the smaller into the larger, it's known that it's not too hard to see that you couldn't be updating something 5 times unless the class has doubled itself 5 times. And every time you merge, you get into a larger one. So anyway, there's this one has a good worst case and also good and an optimum average case in a sense. But there are many other schemes. The point that I wanted to make is that undoing can also be, because we still have saved, this number 3 still exists, and I think it's interesting to observe that if I store the right information about this, I think I have to keep only one or two things. Maybe I need to know P and Q, but to make P inequivalent to Q again, suppose I wanted to undo this operation. Let's see if we can figure out how we could undo it. So we're given the orange, and now we want to get back the yellow. So P is so if I swap the if I swap the pointers of P and Q again, then that would give me my original two rings.
You still have your old pointer from Q around?
Hold on to it.
Yeah, I would keep in a data structure P and Q, saying that was one of the things I did. In other words, I would keep an undo data structure which would have operations that I changed to values. So that would be setting P to 0, setting P to 1, setting P to Q, setting P to Q bar, and then I would know how to undo all four of those operations.
Even if you didn't, you could still wander around the second ring until you came back to the... Oh, wait a minute.
All right, so...
You do have to keep a pointer to the old header.
Yeah, somebody has to remember
Yes,
where that one was.
Oh, well, with your change, you could say that one of the things you did was P equivalent to Q, and then also store the header.
Okay, so what if I stored just P in the header? Could I figure out what Q was? No?
Well, you can go just 3 around.
Yeah, I know what. See, the header still contains the number 3. Nobody diddle with that. And so it's 3 steps from the beginning. That tells me what Q is. Because P is pointing here, and I can be changing all these guys to point to the old header, and I'll find what Q is, and then I can interchange the pointers to P and Q. So remembering P and 3 on my undo list would be sufficient
You have to
restore
undo
the
in the
data
order.
structure, I think. What?
In that, you have to undo in the order that you...
Yeah, reverse order, in backwards order, yeah. So you have a stack of things to undo, and you go back. That's a good point. If you try to go it the other way, you'd be in trouble. So you undo in last in, first out order. Yeah. Okay. Now there might be other. It might be just as easy to do undo other union find structures, and I have to add to this the extra complication of negating bits. And it turned out that the representation that I had there might be other. It might be just as easy to do undo other union find structures, and I have to add to this the extra complication of negating bits. And it turned out that the representation that I had sometimes didn't restore this structure exactly in the sense that these bits would either be instead of having like suppose I said that this was 3 and this was 3 bar and this was 3 bar. It might, after I restored it, it might be that this is 3 bar, 3 and 3. I think in my data structure I might have reversed the sense of an equivalence class, but that didn't. I don't think that matters. And I just changed the. All that matters was the relation of things to each other, but not whether or not all of these things. If you complemented all of the bits representing, if I change that one to this one instead, that would have a different representation, but it's equivalent for processing purposes. And I think after undoing mine, I didn't know the difference between these two, and I might have restored this one as this one, something like that, but it didn't. But it shouldn't matter. Yeah, Mike?
What troubles me is I don't see how to use this sort of representation to represent all the information that you get. For instance, if you have an OR whose output is 1, how do you express the relationship between its inputs?
Okay. Now, if I have an OR whose output is 1, how do I represent the thing of the inputs? And that's we haven't got any information there. We know if one is 1 or the other is 1. And it's an OR, and I haven't covered that. That's right. If I have an OR that's output is 0, then we can push that back to the inputs, and we can push it forward. But there's some kinds of feedback that we haven't done yet, and that's a problem that I'd like to leave until Thursday. Has a very interesting solution too, at least one interesting solution. But what time is it now?
12:01.
We could talk about that now, but I wanted to finish any other data structure issues. Let me see. So if somebody, one of the points then that you could do, I don't mean to force this on anybody. I'm saying this is one way to represent equivalence class. I think it's valuable to consider 4 kinds of values. Incidentally, in this case here, this particular representation happens to have the property that on an input or an exclusive OR AND, these things that have values, the operand is a pointer to where it's used, and the aux field hasn't been mentioned yet. On the case of a fetch, the operand is it says where to fetch it from. The auxiliary is the next place where this input was also used. So, in other words, in the previous place where the same value was fetched is here in the case of the fetch. But then we have the aux field to use on these other guys for values. So you could have the value here of value of values on the in these particular fields. Fetch we don't need values. And here we could, here we have the value of the gate, the known value of the gate so far. And the value of the gate so far is of 3 kinds. It's either known to be 0, or known to be 1, or known to be a member of an equivalence class. Initially, all the gates are in an equivalence class of size 1. They're known to be equivalent to themselves, and so this gives a this value, for example, you could represent it the following way. 0 could represent 0, 1 could represent 1, and the numbers 2, 3, 4 could be headers, and -2 could be the negative of the header. In fact, I believe what I did was I represented 0 as -1, so that complementing was always taking the negative of a value. So -1 represented a gate value of 0, and 1 represented a gate of 1, and then -3 and 3 would be values that are known to be negatives of each other. But -3 and 4 are values that are uncorrelated with each other. And then you could build subroutines that would manipulate these values and being able to undo the manipulations on values. Now, let's see. The next thing is to say what kind of manipulations do we do on values, and that's to introduce what we would talk about on Thursday. We had there's several problems to work out. One is to figure out what the whole goal is of whatever we're working on at the time. Is we might be trying, for example, to well, let's state the following. Suppose we have suppose I have my complicated DAG, and I want to find a set of inputs so that specific gates are known to have certain values. I guess that's one reasonably general subproblem. So suppose I want to say that, say, gate 5 is supposed to equal 1, gate 6 is supposed to equal 0, and gate 11, or let's say 300, is supposed to equal 1. And now I want to find inputs for the, and suppose I've decided that this is a subproblem which I'm interested in. I'll find a set of inputs, a general set of inputs for which these have the property. Okay, now this is our starting thing, and it's very much like a theorem proving problem to tie it in with other kinds of heuristic search. That is, I want to find some axioms which are values of the initial variables. Axioms: x0 equals 1 might be an axiom, x2 equals x3 might be an axiom. I want to find a set of axioms from which these are theorems. So these are unproven theorems, and I wish to have a way of verifying, but because the x's are there, I want to have a way of verifying that these are theorems. And thinking of it as theorem proving is, I think, a very helpful way to look at, because you've got some things that are known to be true, and some things that are assumed to be true, and some things that apply other things. But if you mix up what's assumed and what's known, it can get very confusing. So that's the issue that I think everybody has to confront for themselves in order to understand it. You don't just you don't just understand it by hearing about it or seeing somebody else do it. You have to be confronting with that yourself. That's why I don't want to talk much about it until you've actually had a chance to think about it. But when we do say that G5 is 1 and G6 is 0, one of the things we'll say, suppose G5 is an AND gate and it's 1, then we know that both of the inputs to G5 have to be 1. And so we're going to have to set as a sub-goal to prove that the two inputs are equal to 1, because G5 is one of our goals. Now if G5 is, but we could also, since G5 someday will be proved, we could also use the fact that G5 equals 1. Suppose G5 is the input to an OR gate, then we know that OR gate is equal to 1. G5 is an input to an exclusive OR gate, then we know that we got an equivalence relation of the output of that exclusive OR gate and the negative of the input, and that'll be a consequence of what we will prove someday. So the general idea is that you can solve a problem like this somehow or other, manipulating values, saying that certain things are forced to be true as a consequence of things we've proved or someday will prove. Other things are assumed to be true, or sub-goals are added to the list of things to prove but those list of things to prove are also represented by values. Say, prove that G5 is 1. That's 1 is a value. Prove that, another sub-goal might be prove that G3 is equal to G4 bar. Okay, so now when you get to an OR gate and you say G6 is 0 and G5 is 1, but that's an OR gate, then you've got two sub-goals. You can you suppose its first input is 1 or its second input is 1. And so you've got to bite the bullet and say, well, let's temporarily assume the first one is 1. And if that doesn't work out, undo everything, backtrack, and see if the first input is the first input is 0 and the second is 1. Now that takes time, because every time you split your problem into two parts, you might be doubling the amount of time you spend on solving the problem. So it's advantageous to do all the forced moves first, to do all the deductions that don't require branching, and carry out all consequences forward and backward as far as you can. That's why an equivalence scheme like this gives you a lot more things to propagate without branching. Yet then there comes a time when a branch has to be made, and there's the question as to which branch to take, and to try to minimize the amount of the amount of branching that's done, the total amount of computation. Usually, if you put a lot of, it pays to put a lot of extra computation into cutting down the number of branches that you have to do. Andy?
Well, couldn't you also use some forward, that would be backward chaining, but couldn't you also use some forward chaining to kind of reduce the search?
Yes, like forward chaining, for example, you mean what?
For instance, to force a gate near the top of the circuit, a gate that's not nested too deeply to be 1 or 0, you can explicitly compute, as we did it a few sessions ago, which patterns of inputs would force it to a 0 or a 1. So if you've already forced some of the inputs to be certain things, and you get to a gate and you want to know if you can force it, you see if the current set of inputs is compatible with the set of inputs that would force the gate to be the 0 or the 1.
So what I was envisioning is that I have a value structure here now. In these with each gate, every third position in this section and every position here, there are values on these things, and there's relations between values. Whenever I know that an AND gate is 1, then I know that its inputs are both 1. Whenever I know that an XOR gate is 1, I know that its inputs are both complements of each other. Going the other way, if an AND gate is 1, if an input is 1, I know something about the other, about the value of it. And if two inputs are complementary and I'm taking their AND, I know that the AND is 0. If they're complementary, I'm taking OR, I know that the OR is. So I know relationships on these values, and given any set of values, I can explore that to its completion, right? Its closure. All of the consequences of any set of values in the value structure, so, for example, as you mentioned, the inputs, I might know that some inputs are there. Well, those can propagate forward all the way to say that we'll know a lot of the other gates in the circuit too. Incidentally, there's a way, but if I was starting with this subproblem, it might turn out that in order to make these three true, that I need only 10% of this DAG, and it would be a big waste of time to be propagating inputs that are never going to affect G300, for example, to gates there. So I believe I think I started out by if I was ever trying to solve a problem like this, I immediately subsetted my DAG down to the gates that were really going to help me since it'd be a much smaller circuit. If I didn't need the whole circuit, I didn't have to do forward propagation into things that were never going to be of interest.
Did you pre-compute that in some initial pass, like store with gate 300 all the things that affected it, or?
Well, we got that. You can work back from 300 all the things that. Yeah, so you could, for example, you have another array, for example, in this structure. You can use, of course, Lisp and so on. Right. If you start out with a certain number of gates that are marked, saying I know I want to use these, so you put a check mark there. Well, then you scan back, and every one that's marked, you mark its inputs. And then at the end, you've got everything marked that's relevant. And so you don't propagate forward to anything that's not marked. See what I mean? It's like garbage collection, I guess.
Essentially, did you actually use this data structure in your program?
Yeah. It's just because I write programs in web nowadays. They haven't made a web version of other for other languages here yet. But this is the my current hobby horse is programming in with documentation as well as alternating documentation with code. Yeah, you want to see an example? Let's see. Why don't you? Yeah, Ramsey, can you hold this up for the guy? We've only got 2 minutes left, but I want to show 2 things on the screen, and then we'll go on, and then we'll go off, because this was just to give you an example of how okay, this is the way a web program looks. It starts out, there's some documentation. Here it says 65. Now we come to the point. A heuristic for choosing what subproblem and so on. Function choose is described. Move up now, Ramsey. That's good. Okay, that's longer than I usually write in the web module. Usually I try to go to about a dozen lines, and then these will usually refer to like here it says do complex calculation for output LL 66. Then you go to 66, and it explains what that means. And I find it the fastest way to write programs and get them going in a hurry. It says this code is used in section 65, and so I alternate documentation with program. Here's an example of the proofs that it produces. Here we go. Trying to prove values. This is from the middle of a proof. Trying to prove values at 811, 817, level 0. That's level 0 of backtracking. Setting 559 true, setting 661 true. Need to prove 559, need to prove 661. These are sub-goals have to be proved. Proved 811, that 559 and 661 are true. Making 655 equal minus 568. That's an equivalence operation. Need to prove 655, so on. Anyway, at the end it said, prove this. Let's see, at the bottom, do we actually come out? Branching on 599. Something is true. And it just did a long test, and finally it said, okay, so finally I had a solution. Here, let's see. This is the climax of the thing here. You got, how are your arms doing, man? Go up. Go up, go up, go up. Here it is, here it is. Whoops. No, higher. That's it. Right here, look at this. 2, minus 1, 1, 1, 1, minus 1, so on, and works. This means I found a solution. These are the 16 inputs. This one is equivalence class 2. It can be any value. This one is a negative 1 plus 1. That means it has to be 0, has to be 1. So that was the solution to the problem. That did it. I didn't need to know x1 in this particular case. Okay, that's an example of what a program might look like if it put out a stream of consciousness at the end. Just as an example of one approach. That's fine. Good. Okay. And I didn't know exactly how to handle discussions for this one because there are many subtopics to do. So I put these examples in here just to get your mind thinking. But probably on Thursday, some of you will have a better way. So we'll talk about on Thursday how you've done it. Good. See you then.